I don't even need this identification. I can just hear recording in progress. Uh, yeah, hello. My name's not on the slide, but I'm Daniel. You all know me. I'm here to talk about Chapel Pi, which is a layer of Python bindings for our compiler reimplementation, Dino. So I thought, I would give as much context as possible just in case. So I will talk about what Dino even is before I launch into a motivating kind of just a sequence of motivating things for why we built the Python layer. I'll then give a brief tour of its functionality so that people know what they can use it for. And finally, I'll delve into the implementation detail. These slides have the unique privilege of never having been spoken to before, so I might not be able to get through all of them. I usually over-prepare slides, but hopefully that means that we can focus on what we need and have the right amount of material for that. Right, so let's talk about Dino. So you all probably know, but if you don't, well, Dino is an effort to re-implement the production compiler in a more maintainable way. And this effort started mostly because Chapel's compiler began as a research prototype and evolved rapidly and in many directions under tight time pressure and the desire to ship new things. So the old compiler has like a kind of a small set of primitives doing a lot of work, and it doesn't have any particular focus on developer tooling. But modern users, when they use the programming language, they want lots of things. Well, first, they want it to compile fast, which we don't really today. They want nice error messages, which we're getting better at even in production. But languages like Rust and Elm really set the bar for nice error messages. And they also want editor integration. So they want to open VS Code or Vim and be able to hover over things and autocomplete and do all sorts of things. And usually that requires language support, which the legacy compiler or the production compiler does not support. So with Dino, we went to re-implement the compiler front end, which is the parsing and type checking part, basically, in such a way that we can write it as a library and a representation that will help us achieve these multiple goals instead of just compiling the program. Dino today is used in production for scope resolution. I'll talk about what that is just a bit later on. And it can almost do type resolution, but it's not quite to the point of replacing the production compiler's type resolver. So when you want to support tools, the language server being one that we'll talk about a lot, and that's kind of the motivating example for a lot of our tooling work. There's many assumptions about that like held in the regular compiler that you can no longer assume. So you can't exit on error when something goes wrong. Like if an error occurs, you can't just say, this went wrong, bye. Because editors expect the language server to be a long-running tool that continues existing pretty much as long as the user is editing a file. So it needs to persist, kind of grit its teeth and keep going. You also can't fail for just completely garbled programs. So even if the user, invokes some kind of internal compiler primitives or writes completely nonsense code, you have to tell them that they wrote nonsense code and carry on. Also, a regular compiler invocation compiles a single project notionally, but an editor can work on multiple projects. You can open 15 of the same file in different folders. Like you can have 20 checkouts of Chapel and open the same file in all of them. And the production compiler just wouldn't, or a regular compilation would balk at this, but the tooling must be able to support it. And also, you can't assume that you're just doing a one-shot compilation or resolution. So you typically users edit a file really rapidly, and some people have their editors configured to save on keystroke, and they want updates about whether their program is valid, whether there are any errors as quickly as possible. And the production compiler just isn't well suited for such a thing. So Dino addresses these in a few ways. Basically, it puts all mutable compiler state into a context object, of which there can be multiple. So there can effectively coexist multiple compilations of things without destroying any global state and allowing you to rerun compilations without much trouble. It also provides an incremental resolution engine, which means that it can compute just the right amount of results for you for whatever information you're asked for, and not any more than that. And it can also recompute information as your file changes without having to do too much of the work redundantly. But this incremental resolution engine and the architecture that it entails means that Dino's data structures are typically immutable. So they have getters, but they don't have setters. You can read them, but you can't write them. It turns out that this is pretty nice for creating a Python implementation, and I'll talk about that in just a little bit. Dino also takes more care to be a user-facing C++ API. It provides lots of features for parsing, resolving, and doing all sorts of things with the program as if it were a library for the compiler. Okay, so we have a C++ library, and we can write tooling with this. So why should we use a Python layer? Oh, Brad, go ahead.
Yeah, I didn't mean to interrupt you mid-sentence, but I was curious before we transition out of Dino. I was just a really high-level question. Based on sort of Dino's goals and your experience with it so far, um, do you feel like were the decisions made, the architecture, things like that, do they feel like they were done well and correctly and they're sort of supporting the goals? Or do you feel like there are things you're like, if I could go back and sort of change or fix something about Dino, I might do this instead of that or anything like that? Just at a high level.
Um, I think overall Dino is very well designed. Lots of things kind of followed naturally from the initial plans for the engine. I think the biggest challenge, if I had to name one, is the fact that normally we rely on like a lot of recursive algorithms within Chapel, and the language is highly recursive. So, you know, you can have mutual dependencies of modules and all sorts of things like that. But like the caching and incremental recomputation engine does not support recursion very well. In fact, infinite recursion, it just breaks it. And guarded recursion is hard because all queries have to be stateless. So you can't have like a visited set of things that you've traversed in a dependency graph. The result is a couple of hacks that technically break the recomputation engine and in general can lead to problems. They won't actually occur when Dino is used as a, compiler backend or compiler front end, but they might occasionally bite users if they start editing standard module files or something like that, which they oughtn't. And it's very hard to work around that. I don't know how to fix this in general. I think it's part of the problem is the language is complex, but I think that's a challenge with Dino that we have right now.
Okay, great. Thanks very much.
Cool, thanks. And yeah, so anyway, why make a Python layer, and why did it turn out good enough for us to use it? Well, let me give a little bit of historical background. The reason that we even care about this is that we wanted to implement a very specific kind of tool for Chapel, which is a language server implementation. So a language server protocol is a standardized way for editors to learn how to provide intelligent suggestions, autocompletion, etc., for languages. So basically, an editor learns how to ask the language server questions, and different languages provide their own language servers. And that makes it easy for any editor to talk to any language. And we wanted to make a Chapel language server so that editors can provide helpful suggestions for Chapel. And we basically had two approaches. We could use Dino's C++ API to write the language server. Well, we technically could have also used the production compiler, but it's a bit of, like I said, the architecture wasn't well suited for writing tools. So the next best thing is to use the C++ API to write a server based on Dino, or we could use C++ to develop a Python bridge and then write the server in Python. And honestly, this is not an obvious choice at all because the engineering effort to create a Python bridge is potentially unbounded, and it's not clear that we would win from it. But on the other hand, Python does have better library support, so we might be able to, in theory, get some help from Python. But in terms of portability, complexity, and kind of the amount of work to be done, it was not clear that Python would win. So we initially started to write the language server in C++. And either ahead of time or after a little bit, we found that C++ was somewhat challenging for writing tooling. So for one, it's the wrong level of abstraction. So we're talking about managing memory, moving data around, heap allocations, pointers. This is really not what you want to reason about when you're writing a tool. You want to reason about data representation, maps, things like that. C++ also has significantly worse library support. Like there's still no canonical way to import a library in C++. You can use package config, you can use some kind of find whatever library CMake module, you can copy the library. You still need CMake to describe how to build your program or some other kind of build script to figure out how to link your C++ project with others' dependencies. And for the language server protocol in particular, that I recall, we didn't have any mature C++ tooling for writing a server, so we had to roll our own. And then things that weren't really obvious to us in our initial analysis, but turned out to be kind of problematic, is that first, C++ doesn't really have support for testing LSP-based tools, LSP here being the language server protocol. So if you wrote a language server, you would have to also write your own testing framework, which actually the team spent a decent amount of time doing, which was not productive, I think, because, well, it's not productive compared to the alternative of Python, which has Python PyTest LSP, which lets you just hook into PyTest and run language server tests. And C++ also has worse support for dynamism. I hope I'm pronouncing that word right. But in general, it's harder to write high-level abstract utilities in C++ because at any given time, you need to know something's compile time representation. And also, C++ can't easily dynamically load new code. So we actually take advantage of loading code dynamically in the Python world, and I'll talk about that in just a bit. And then, this is actually a picture from a presentation that I gave when I first introduced the Python bindings, which is, well, who, when creating a new C++ project, wants to write the make files, bundle the required C++ libraries, maintain C++, and that kind of boils down to not that many people. But then, and that also from my presentation introducing the Python bindings, with the Python bindings, with Python in general, you can do a lot very quickly. And this guy is like flying because he imported anti-gravity. And that's kind of the approach that I hoped we'd be able to get to with the Python bindings. And I think that turned out pretty well. The initial proof of concept for the Python bindings was a linter for Chapel, which is now called Chapel Check, and it's one of our canonical tools. I have on screen, I believe, a verbatim rule from Chapel Check, which flags any declaration that starts with the prefix Chapel outside of Chapel standard modules, so that users don't write code that starts with Chapel, which is a reserved identifier or a reserved part of a name. So you can see that this is maybe like, 6 lines of Python, which says, hey, this rule should apply to all name declarations. And if it's in a bundled path, it's okay. But if not, then we should warn about it. And so it's this kind of brevity that really cements the power of Python bindings for us. On top of this, we can use pip install and just import any library that we really need. So we have PyGLS or PyGlass, which is used for implementing language servers. We have PyTest LSP, which is used for testing language servers. We have LS protocol. I'm really hammering the language server here. But we have LS protocol here, which is an automatically generated set of type definitions from the specification of the language server protocol. So we can knowingly and correctly use the right types. We can import PyYAML to parse and write YAML files. We can import config argparse to allow our tools to be configured from both the command line and some configuration files, and so on and so forth. We can also dynamically load code because Python is a dynamically evaluated language. In Chapel Check in particular, this allows users to write custom linter rules and for us to just load them. And this is used in both Mason and Arcuda. And finally, although creating a whole another interface for Python based on a C++ bindings is kind of expensive, the fact that the C++ API is immutable makes Python pretty well suited for a read-only interface, because all we have to do is provide wrappers to the data structures on the Python side and accessors for their data. And here's just a couple more samples. This is a post-order iteration procedure written in Python. So we have this is a generic procedure that when you give it a node in Python, it will iterate over that node in a post-order fashion. And it's what, 3 lines of Python code, basically. And as another example, one of my PRs some time ago used a Python script, throwaway script of maybe 30 or 40 lines to find a bunch of issues with our standard modules and automatically adjust them. Okay, so that covers the motivations for using a Python bridge, and I'm now ready to talk about what the Python bridge is capable of. Like I said earlier, just interrupt me if you have any questions. I'm not reading the chat, and I'm here to talk about whatever.
You're not missing anything in the chat, don't worry.
Okay, cool. Okay, well, I'll talk about what the Python bindings can do. So the initial and most common use case is just inspecting the AST. So the code here isn't actually how you inspect the AST, it's what the AST looks like. One thing about Dino that differs from the production compiler is that Dino contains many more AST nodes, AST being the abstract syntax tree. We'll talk about that in just a little bit, compared to the old representation. And they're more precise. So instead of just a general call expression node as in production, Dino has function calls, operator calls, primitive calls, and even zip, which is the thing that you use in loops to zip multiple arrays together. And this representation in Dino is mapped one-to-one to a Python representation. So here we have a call class in Python that extends from the AST node class, and a function call class that extends from class, and so on and so forth. So here's an example of Dino's AST. The program I'm looking at here is one which stores 1 plus 2 times 3 into the variable x, and then prints x. So the top level AST node here is a module, which contains, so all Chapel code is in some module, basically, and that's why the module is the top level node here. The module here is implicit, but it's there. Then we have a variable node, which corresponds to this variable declaration for var x. And one of its child nodes is an opcall plus, because we're adding 1 and the result of multiplying 2 and 3, which is encoded by this opcall times 2 and 3. And the second child of the module is the second statement, which is the write-ln, and that's just a function call where the function is write-ln, and the arguments are, there's only one argument, and it's x. And so in the Python interface, this is the first complete, I think, Python interface program that I'm showing. You can basically achieve reading the AST in very little effort. So like I mentioned with Dino, we have a context object, which contains the compiler state and a bunch of other bookkeeping information. So all Python interface users have to create a context. Once you parse any given file, you get a list of modules out of it. And then we can use the standard utilities, such as post order, to iterate the modules in a post order. Basically, a post order means visiting the children before the parent, but visiting the entire AST. And here, what I'm saying is I'm using a normal Python isInstance call, which checks if a particular node is an instance of a different class, to say, well, for any node in this tree, if it's a declaration that has a name, print this declaration. And so for the previous code here, the Python snippet that I just showed would print only x, because x is the only declaration in this program. So I have to give a little bit more context on context. So like I mentioned earlier, context contains all of the compiler state, which is important because you can't have global state if you want to be able to compile multiple files or recompile something many times, et cetera, et cetera. By Shreyas, I think. So this includes loaded files, compiler configurations, et cetera, et cetera. It also contains a bunch of kind of internal state for incremental resolution and recomputation. This is kind of not visible to the user because the user just says, what's the AST of my file? Or what's the type of this AST node? But internally, we have to keep mutable state that says, have we already computed this? If so, where do we store this data, et cetera, et cetera. So you can almost think of a single context as mapping to a single invocation of the compiler, except the context can let you rerun the computation once the user edits some of the files and reuse some of the work from the previous invocation. So it's not quite the same as a single invocation, but it's almost there. And for the most part, this means that the context still has assumptions about a single program being compiled. The most notable one that we ran into before is that only one file with a particular name can be loaded, which is kind of a restriction that we've had in the past in the compiler in general. So you can't have 15 files all called a.chapel because then, import a suddenly starts to lose its meaning. And I'll just mention that there is a utility within the Python bindings that helps you create enough contexts that all of them have unique files. Well, that all of them don't share any file names from a list of files. Brad, I see your hand.
When you say like only one file with a particular name, isn't I would imagine it really to be one module with a particular name or multiple files with the same name that are relying on the sort of file name becomes the module name concept, right? So if I had 15 a.chapels, but each one explicitly said module M1, module M2, whatever, would that be problematic or not?
I think it would be. I shared your intuition. I initially wrote this as only one module name, but I am pretty sure that I recall Dino having specific restrictions for a particular file. So basically, like if you say load file with name, whatever file it reads first will be the file that is loaded with that name. And if that file is from somewhere else or its path doesn't match, I think you will get in trouble. So I'm pretty sure, at least on the Dino front, this is a file name based restriction in addition to a module based name restriction. But in production, I'm not so sure.
Okay. And do you view that restriction as like a sort of implementation wart, or is it something sort of deep and necessary for some reason in Dino?
Uh, Hard to tell. I think it might be an implementation wart, but if it is, then it's the most natural way to implement the query system together with files. Like the fact that we have a query system, which is the thing that takes care of the incremental recomputation and incremental and memoized computation has some weird consequences, and I suspect that the file name thing might be one of them, but I haven't given much effort to writing it without this constraint, so I can't say for sure whether it's a hard constraint or a soft one.
And if that were sort of the motivating reason, if we used kind of a normalized absolute path instead of simply the file name, like would that get us to the same place while, making distinct files unique?
So we do use an absolute path, but I think the problem is with the mapping of module names to file names, which has to happen occasionally. Um, and I think it's there that we run into trouble. So like,
Huh.
yes, we store files for the absolute path. That's fine. But then at some point you need to be like file for name a.chapel, right? Um, and if that like then suddenly, well, how do you find a.chapel, right? You have to have read a file called that from somewhere else. And then suddenly, and because like having found a file is a memoized computation, you lose the ability to kind of change what file refers to a.chapel halfway through. And I think that's what I mean by consequences of the query system. But like I said,
Okay.
I haven't looked very deeply into this, so I'm not sure if there is a better approach. Of
Okay. Okay. Yeah, that's helpful for what I was curious about. Thank you.
course. Yeah. So, and then, if you don't want to spend the time improving this work on the implementation, you can use this helper procedure from the Python module implemented in Python, which buckets files into multiple contexts, such that if there's two files with the same name, they get different contexts. uh, The Python API also exposes a pattern matching syntax, which is not used in huge detail nowadays, but in theory is pretty powerful. So here, the pattern pat on the first line specifies a function with exactly two formals, both of which I think have a type expression, which is an identifier. So like f1 int, actually, let's see, yeah, formal like f1 int, although the name is not actually constrained by this. This is a pattern variable. Uh, so like proc f with an x colon int and y colon int and some body is matches this pattern, but lots of other things don't. And you can invoke the match pattern procedure to check if an AST node matches that pattern and also to extract variables that you've named, such as in this case, the formals, into a dictionary. So that's cool. Mostly we use very simple patterns like just the class of an AST node, like function. But in theory, you can do more. Before I keep going, I want to talk about unique IDs. So Dino uses unique IDs to identify nodes, and it's pretty much the main way that it does this identification for reasons that have to do with being amenable to recomputation and incremental re-resolution. And a core assumption is that IDs only exist if a corresponding node already exists, with the exception of the empty ID, which refers to no node. And the C++ API has a function that maps IDs to the ASTs that they represent. On the Python end, we run into a little bit of trouble with this. So sometimes we need to send IDs over the language server protocol or store them in basically JSON. And the problem is that once you start reading it back, you can no longer make that assumption that the ID that you're reading back corresponds to a node because you're just parsing it from some user input. And that's a little bit dangerous. And on the other hand, if you're not making a round trip through the language server, then why do you even care about IDs? You can just look at the AST node directly. And the net effect is that in C++, where IDs are used, the Python interface basically just directly refers to AST nodes where possible. And you can query IDs if you want to like store them in dictionaries or something. But if you say like, what node does this refer to? It won't give you an ID. It will just give you the AST node. And on to talking about what node does this refer to? Dino powers the production compiler's scope resolution, which is the process of mapping names to the declarations that they refer to. So for instance, if, oh, well, we can even look at this. We can go back here for a second. So scope resolution would say this var x refers to this declaration of x on the first line. And ChapelPy, the Python interface, exposes this basically using a two-node method, which gives you the node that a given identifier refers to. So it doesn't convert it to a node, despite what this name might suggest. It is the equivalent of a C++ property called toID, but it's actually a higher level wrapper. And in C++, it's harder to do this, but we provide kind of a convenient wrapper to enable this operation, which turns out to be pretty common. So as a little demonstration of scope resolution, here's a watered down version of a linter rule called unused formal. This rule says, well, if any formal within a function body is not used, we should flag it and say, hey, you should either delete this formal or do something about it. It basically proceeds by saying, okay, well, for every formal node in the AST, save it in some kind of map or dictionary. And then for each identifier that might refer to a formal, well, does it refer to a formal? Compute what it refers to by using toNode, and then save what it refers to in a set. And then for any formal that we found that hasn't been used, warn about it. And this implementation is actually significantly watered down from the main implementation, just because there's lots of corner cases and weird things. But generally speaking, it's what we want. And it's written in, so the watered down implementation is written in like 15 lines of Python code. The real implementation is probably more like 30, but 30 is not so bad. Well, that's most of scope resolution, honestly. The general interface is very simple. Like you can just ask toNode. So I'll talk about resolution next. Resolution in Dino is not yet finished, and it can be used in production, and it is in our language server for type hints and so on and so forth, but it's not completely one-to-one mapped to the production compiler's type resolver. And by the way, resolution is the process of figuring out the types of expressions and also which function overloads are called. Because in Chapel, which function overload is called depends on the types of the arguments. And so the figuring out the types of the arguments is a prerequisite for that. Now, I'm talking about types, overloads, and lots of other things. And that is a whole another dimension that we previously haven't seen Chapel Pi expose. The most obvious thing is that Chapel Pi exposes another class hierarchy like the AST node hierarchy, but this time it's a type class hierarchy. And it contains all the types that Chapel programs can exhibit. And matching the previously mentioned two-node API, Chapel Pi provides a resolve method. Although this is not quite enough, there's a bit more nuance to resolution that we simply didn't have in scope resolution. Before I go into that, though, I just wanted to show. Oh, Brad, go ahead.
You may be getting to this later. And if you do, you're welcome to just defer this. But I was trying to remember when you talk about resolution and the fact that the tools can make use of it. I think in the last release cycle, we were discussing whether we should enable the resolution capabilities in the language server and tools by default or continue to require people to opt into them. And I think we decided not to at that point, but then I think we improved things further. Am I remembering that correctly? And where do you stand right now as to like whether maybe we should have them on by default or not, if they're not?
I don't recall if we ended up doing this. I think basically the conversation was, hey, we should enable this. Well, it fails a lot in Mason. Well, let me fix the failures in Mason. I fixed the failures in Mason. I don't recall if I did much more work to, pull that re-enabling of them by default again. And yeah, I don't know just how stable these are because Jade says that it crashes all the time, but then it's like a Wittgenstein problem, right? Like what is Jade's all the time and what's all the time? And also what's the sort of things that Jade is doing and what's the sort of things that a regular user is doing? I personally run the type resolution by default in my editor, and I rarely have it crash, which is why I was pushing for enabling them by default. Um,
Yeah,
we have a small sample size. Like no one will use the thing and tell us about it, even on the team. So it's hard to generalize. And I think that's part of the stagnation of this effort.
okay. And like so I think you're right that Jade's concerns at the time were largely based on Mason, which of course is what they were working on the most. I feel like I haven't really gotten a read from Jade since you made those improvements, although I feel like what little I've read has or what little I've heard has suggested that that things have gotten better. But that seems like that might be worth taking up again.
Yeah, for what it's
Assuming
worth,
you and Jade haven't had additional conversations that I missed out on.
yeah, I don't think we have.
Okay.
I think it just got pushed to the background. For what it's worth, I think Jade is enthusiastic about this, and like I wouldn't view them as overly conservative in this manner. Like I honestly trust Jade's judgment on whether this should be enabled by default or not.
Uh-huh.
Um, so all that to say, like when Jade comes back from vacation, I think they would be a very good judge of whether. And so certainly we shouldn't do this for 2.9. It's too late for that. Uh,
Right.
but when Jade comes back from vacation, I think they'd be a good judge of this.
Okay.
Yeah.
Thanks.
Okay. So to continue to talk about what I was talking about, I think, which was just showing you the class hierarchy for types, which matches quite a lot the AST node hierarchy. Um, just like the AST node hierarchy, Dino has these C++ macros, which I'll talk about more in a little bit. This is actually a piece of source file from Dino that declares that we have a declared type, a class type, an enum type. And then Python has the matching classes to provide to the user. Okay, so now a little bit more nuance to resolution. So unlike scope resolution, the same code can have different types in regular non-scope resolution depending on the context. So a very simple example of this is a generic function, my function. which adds 1 to x. So when you call my function with an integer, x becomes an integer. And when you call my function with a complex number, x becomes a complex number. And so when you can't just say, what's the type of x? Because the type of x depends on the context. And in particular, the abstraction that we've chosen for the Python interface, and largely for Dino as well, is that you can say, well, here's a function signature with types. For instance, my function where x is an integer, given that context, can you resolve x? And so to make all this work, I have to move my Zoom window a little bit out of the way. To make all this work, we provide a typed signature class to represent a function signature with types, like my function where x is an int. And we also provide a resolve via method, which instead of taking no arguments like resolve, takes that signature and allows the user to use it to get the type of a particular variable. Furthermore, resolve doesn't just resolve a type, it produces a resolved expression because resolution has many more outputs than scope resolution. So in particular, resolved expression can be used to ask what the type of a variable is, but also if you're asking about an expression, it can tell you all the function overloads that were selected, of which there can be multiple, but even asking for the one overload is useful. But there can be multiple because of something called return intent overloading. Then there's all of this is actually false. The Hawaiian dish of poi makes some of these assumptions not true, and there's more details. I will not talk about this, but this slide contains some extra info. So the next thing I'll talk about is that there's actually more than just the AST node and type hierarchies. There are actually, as far as I know, 4 type hierarchies, all of which are documented automatically, and you can read about them pretty much anywhere. And we automatically expose them from Dino. And so the hierarchies are the AST nodes, the types, the params, which are not much of a hierarchy. They're just 5 classes. And also error messages, which are also not much of a hierarchy. There's just a base error message and then a bunch of subclasses. Like I mentioned, they're generated automatically from Dino. And well, Daniel, how do they get generated? That's so cool. I'll talk about that next. And finally, we also generate a Python interface file at this standard path, which contains the kind of a documentation for all the automatically generated methods. And it can also be used in your editor to provide autocompletion. All right, so that basically covers the capabilities of the Python interface. And I am ready to talk about the implementation details. I've saved the, the scariest for last. Now is a good time to interrupt with any questions about what the Python interface can do before I dig into how we make it work.
I have a quick question. Back on the question about enabling resolution in Chapel Pi by default or not.
Mm-hmm.
Oh, can you remind me how static versus dynamic kind of a choice is that? Like just kind of fantasizing for a moment. Like, is it something where with proper engineering and UI, like I could have a little click box which would say like use it or not, or is it something that is a bit more,
Yeah.
woven in and
So
would require more effort?
the Python interface always includes support for resolution. It
Okay.
always is triggered by calling a particular interface or like a particular function, and by default, it is left alone. The place where it's actually turned off is in the language server, where certain branches of the language server will not use the resolver if you don't ask them to. That's a dynamic setting. It requires restarting the language server, but that's fine. So in VS Code, there is pretty much a checkbox that says use resolver features. And
Oh,
right
okay.
the checkbox is false by default. But in theory, we could make it true by default. And that's basically the only place where it would need to change.
Okay. And if somebody is using it in the checked mode and they run into one of these crashes or bad cases or whatever, like how bad is that and what is their recovery? Like, do I have the ability to unclick the checkbox and continue, or do I have to restart CLS or Chapel Pi or my editor, or you know what I mean?
Yeah, so I mean it depends on what you want to do. Like if the language server crashes with the resolver, what I do is restart the language server and the resolver is back online. And usually whatever happened to put it in that state is not happening again. Just because, like I said, usually it's to do with incremental re-resolution where problems come up, at least for me. I mentioned there's some kind of limitations to the incremental system which cause this. Anyway, all that to say, like you can restart the server without changing the settings pretty much from the interface in one click. You can also go into settings and uncheck the box, and it will restart the language server for you. In some cases, you do have to reload the VS Code window if you're in VS Code, but that takes all of, I don't know, a couple of seconds maybe. Doesn't lose you any state, and generally speaking, is relatively painless.
Okay. And you corrected my misattribution of the selection mechanism as being, not in Chapel Pi, but in being in CLS. Does Chapel Check similarly have this kind of check, or is Chapel Check strictly so syntactic that like there's no benefit or need for the resolution information?
Today, Chapel Check is purely syntactic and uses at most scope resolution, which makes it rock solid. In theory, you could have linter warnings that rely on resolution. Some of my favorite ideas are like, hey, you've imported used a module, you used use in a module and you didn't constrain it. Maybe you should, use an import instead. Or, hey, you didn't initialize a field. Did you mean to initialize it or something like that? Those
Okay.
are text-based fields, but today we don't do that. And so it just doesn't have that problem at all.
Okay, thanks. Yeah, another interesting one that occurs to me when you go through those examples would be like if you believe that Chapel allows square brackets and parens to be interchanged for function calls and arrays, and if you believe like function calls should always use parens, arrays should always use square, that could be another one potentially.
For
Seems
sure.
like.
Yeah.
Okay, thank you.
Coolio. Okay, well then on to the implementation details. I don't know if I have an hour or an hour and 15. Hopefully the latter, but if not, whatever. I don't know how much people care, and these slides will be available. So, uh, um, okay, well, broadly speaking, Chapel Pi consists of four major components. There are some regular old C++ utilities that pull together a whole bunch of not unrelated, but spread out functionality in the Dino C++ API proper. For instance, I mentioned that toNode does not actually have a Dino analog. We have to implement our own, which uses several ways of figuring out the toNode that Dino provides and integrates that information into one. We also have infrastructure for generating all these types and class hierarchies using Dino's X macros. Hey, Daniel, what are X macros? I wrote about this on my blog, shameless blog, but also I wrote it and it's about Chapel. So honestly, it's as relevant of material as can be. I'll show implementation details, but if it's probably not going to be enough if you haven't heard of these before. And so yeah, we have infrastructure for generating a bunch of C Python types from Dino's header files pretty much automatically without any code generation tools. There's then on top of this a C++ framework for defining methods in wrapped classes and marshalling data back and forth. And this framework in places also uses X macros, but our own X macros. And this helps us map Python methods onto, or things that we expose in the Python interface onto their C++ implementations. And finally, on top of all of this is just some plain Python code that provides some helper utilities for users to use. All right, so the C++ utilities are basically in this one giant file called very clearly resolution.cpp. Resolution.cpp contains a lot of C++ glue code. It includes it includes things that bundle together calls to Dino's low-level helpers, like I mentioned. For instance, toID relies on scope resolve aggregate, which is like scope resolving a record or a class, and scope resolve module, which is about scope resolving a module statement, well, a module, not just the statements. And it also provides some, let's see, what is going on here? Oh yeah, well, in general, Dino provides functions that are relevant to compiling a program, not so much to doing some cool linting warning or something. So if we ever find a piece of missing functionality that's very specific to a tool, we plop it down in resolution.cpp. I think the most notable one is allowing you to figure out in a user import statement what a module refers to. It also implements a bunch of things that aren't necessarily like a core piece of functionality, but are just super tedious to implement in Python. Kind of, oh, I don't even mention this here, huh? Okay, well, I mentioned it eventually, but maybe we'll talk about that. Anyway, so here's an example. Basically, this is a function exported by the resolution.cpp file, and you can see that it tries a bunch of different ways to scope resolve an expression. So it tries, hey, can I scope resolve it using the function thing in Dino? Can I scope resolve it using the aggregate type thing in Dino? And it just, it has like 5 of these, but that wouldn't fit in this slide. And then similarly, there's a bunch of there's like a whole other thing that does similar if else chains where it's like, well, can I resolve this using a function or aggregate? Can I resolve this using some custom logic that we provide, and so on and so forth. So it's this kind of glue code that's contained in resolution.cpp, which backs your ability to say, hey, what node does this refer to, and get a single coherent result without any extra thinking. And yeah, like I mentioned, there's also some utilities that implement tricky features that aren't really that are really just kind of, for lack of a better word, gimmicks in the language server. So for instance, there's a function that takes a generic rectangular array and turns it into, a generic procedure with a, let me start that again. There's a C++ function that, given a signature of a generic function that's generic because it has array formals, which are always generic in Chapel, fun fact, it produces a signature which may not be generic because the generic array formals have been replaced with regular normal array formals, which is most commonly what users want, but technically isn't the full extent of Chapel's power. All right, that's all I have on resolution.cpp. It's just one file, mostly just reading the signatures there is pretty good. It just contains a bunch of glue. So then we have X macro adapters, which basically, well, let me talk about X macro. So we've seen examples of X macros in Dino. I didn't call them out by name, but that's what they were. So Dino has all these header files like UAST classes list and type classes list, which are full of just calls like this: AST node function call, type node enum type. And the way that you use these is you define the macro yourself. Well, okay, not yet. You define the macro yourself, and then you include the header file, which basically boils down to the preprocessor invoking whatever you defined AST node to be for every possible AST node that the header file lists. Like I said, this probably won't be enough to explain how X macros work. You can read about this. It's a well-known pattern. You don't have to read my article on it, but you can just Google this and it will show up. And the thing is that Dino provides several X macro lists. Like I already showed 2. There's multiple. So there's one for UAST classes, which are AST nodes. There's one for type classes, which is for types. They're all slightly different. And so in Chapel Pi, we have a single file called generated types list, which does something similar, but basically notionally calls the macro generated type for any of the types that we automatically bring over from Dino. Cool. So here's an example of how this works. Forgive the code highlighting for making this impossible to read if you have problems with contrast. So here I say, well, the define pi type 4 macro basically just creates a global variable of a pointer to a Python type object with some specific name that has to do with the type. And then I basically define generated type, the macro that's invoked by my header to call this define type. And then I include the generated types list. And the net effect of these 3 lines of code is that for every single type that Dino exposes, we get a global variable declaration with that type. And then there's a note about why we do this and why it's equal to null here, but I'm not going to talk to it too much. In fact, I won't talk to it at all. So the key property that we have with the X macros is that the types that we expose from Chapel Pi always match those of Dino as long as the version of Dino that was built matches the version of Chapel Pi, which is pretty much always. Um, so if a user adds a new type to Dino, or if a developer adds a new type to Dino or a new AST node to Dino, the next time you build the language server, the Python bindings, that type will be available to the Python interface as well. However, these hierarchies so far only expose the types and not the methods that these types have. And this is because these are not really mapped one-to-one, and also because we don't have X macros for them within Dino, so we have to list them in a different way. But we have gone pretty heavy on this and settled on a kind of not a novel, but a specific way of defining these methods on classes, which is another set of X macros. And these live in different header files like UAST methods and for methods, and the method tables header brings together, just includes all of those. So here's an example for the attribute class, or for the attribute group class. I define a method called getAttributeNamed, which takes a string and produces an AST node or none in Python. And the C++ types involved are the Dino unique string type. It can also be a construct pointer, but unique string is what we use more often than not. And then produces an AST node pointer, which might be null. And if it's null, it gets automatically turned into a Python none. And then, here's an implementation of how this happens. You just write return, and then the Python code that implements the method. So the method macro is more powerful because it allows you to specify arguments. But most of the types or most of the methods that we invoke in AST nodes are just getters. Like, is this thing unstable? So for the attribute group, for instance, the isUnstable method just returns isUnstable. So the plain getter macro lets you just write the return type, which is bool, and then have this method automatically generated. And yeah, so what do I mean by automatically generated? Well, X macros, the whole reason they're beneficial is that they let you have one single source of truth and then reuse that source of truth in many different places. So from these X macros, we generate forward declarations in C++. We also implement the methods using the bodies that we saw in the previous slide. We also generate a bunch of CPython boilerplate that registers these methods with the Python objects. And we generate a Python interface file that can be used by you to read the documentation or by your editor to provide autocompletion for the method. And let's see. And so basically, we can also generate a code that takes care of wrapping and unwrapping Python types into C++. So you just write, get the first argument, return node, but the framework takes care of creating the Python object that corresponds to these things. So here I have a visualization. So here's a single plain getter. The isUnstable, which is the name, is used for lots of things: forward declaring, documentation, implementation. The return type is used basically for documentation and for automatically creating a Python Boolean object. And then the body, which is return isUnstable, is just used for the implementation. But so basically, we really make big use of various parts of each of these macro calls. And then the last bit is that we provide an automatic conversion framework that knows how to map C++ types to their Python equivalents. So Boolean to bool, int to int, C++ const char pointer to Python string. We try to do this automatically wherever possible. As you can see, as long as you specify the input and output types in C++ in your code, that's enough for the system to know how to convert them to and from Python. This mapping is bidirectional where we can make it bidirectional because, well, you wrap C++ objects in Python all the time because anytime you call a getter, great, please give me the Python object. And sometimes you want to unwrap Python things into C++, such as, for instance, when we had this argument of unique string to the method getAttributeName, but also in other cases. All of this stuff, these are not X macros, these are just regular old macros, and they're defined in Python types.h. And then we have a Python level framework. Like I said earlier, I don't actually know how long I have. I'm running out of time, but it provides a bunch of common utilities, much of which we've already seen: post-order and pre-order traversals, pattern matching, a traversal that pattern matches pretty commonly. We have some helper functions that are used for custom language tooling, like parse attribute, so that you can parse attribute groups on nodes. There's a bunch of common enough features that have to do with the language server, such as converting ranges to tokens, which are kind of a language server specific thing, I think, and ranges to lines, which is less specific. But there's also way more LSP specific things. And finally, there's a replacer script generator called chapel.replace, which is near and dear to my heart, so I will take this time to talk about it. The idea with chapel replace is that you basically want, and this is mostly useful for us developers and not really for end users, but it's come in handy for us as language designers and language shapers. It basically lets you say, replace all instances of this with this automatically. And so in this, whatever, 8-line script, I say, okay, I want to find every single integer literal. And if that integer literal has the value 42, I actually want to replace that integer literal with the words meaning of life. Then I invoke this run procedure, which I import from chapel replace, give it this thing, and I get a command line script, which automatically replaces all integers with, all integers whose value is 42 with the word meaning of life, and that I can just invoke. And I quite literally I use this many times. So for instance, I use this when transforming our legacy this.complete to init this. I basically wrote a script and it went and found all these occurrences across different files. I think I still had to make some tweaks. And I've done this several times now. So this is, I think, pretty useful and worth knowing about. And yeah, well, that's chapel.replace, I guess. I've plugged it enough. You can read the documentation if you really want. And I'd like to conclude by talking about all the places where ChapelPy is used, so you know that you need to know about ChapelPy for these things. So the language server, the linter, a find undocumented symbols script that Jade wrote, or I think it's Jade. It might have been Shreyas. I'm not sure. Regardless, these two, this script is, I haven't seen it used anywhere, but I've heard lots of talks about it, so that's cool. Or lots of conversation about it. And finally, on the blog, we have a link insertion infrastructure, which automatically plops links into code blocks, and those links lead you to the documentation of the highlighted things. And that uses the Python bindings with the resolver. And wow, would you look at that? That's all my slides. If I had an hour, I'm only a minute over. If I had an hour and 15, then I'm 14 minutes early, but I will not fill up that time. And Brad, please go ahead.
Doesn't ChapelDoc also use ChapelPy?
It does not. It's a C++ based thing.
Okay.
In my ideal world, it would. But I looked at it. It's like, 3,000 or 4,000 lines of C++. And I was like, well, I'm not rewriting that myself.
Okay. So it was rewritten to use Dino, but to use Dino directly rather than through ChapelPy. Is that right?
Yes, that's right. And that's because ChapelDoc precedes ChapelPy by maybe a year.
Okay. Okay. I had forgotten that. Thank you.
Well, now is the time for further questions, if any, because I've gotten through all my material.
Yeah, this is really helpful. I really appreciate you taking the time to put it together and walk us through it.
I'm glad.
Anybody have any questions for Daniel? I could also stop the recording if people want to ask questions off recording. Anna, go ahead.
I don't know if mine has value for the recording, but it is fine. That slide about how we use the X macros to create like the, I think it was the classes for each type in Python. Yeah, the one after this. I was curious about this note.
Yeah, so normally Python would have you create a PyType object as a static thing, basically, like a struct. The problem is that the PyType object, like layout of the struct, can change depending on the Python version. And initially we had a lot of problems with this, where you would build ChapelPy for Python 3.7, And then suddenly you would install Python 3.8 and oh no, it's not compatible. We can't link against this. And Python provides a way to do this without breaking across different versions of Python, which is called, stable API, ABI. I mean, you know this, Anna, but ABI is application binary interface. And the way it does this is basically by heap allocating this data structure for you. And so because it's heap allocated elsewhere, we make it null here and then have extra code that does the heap allocation and populating that data structure at a different time. And Jade took care of this at some point because they were sick and tired of Python breaking across different versions.
So I would assume the heap allocating the PyType object at runtime is done in Python somewhere.
Well, it's in C++. It uses the C++ API. It actually also uses another instance of this generated types list and the X macro pattern. But it's like in main, or in a function that's called from main, as opposed to at global scope, which is what this is.
Okay, interesting. Yeah, I don't really know much about the like Python like C interface, but yeah, okay.
It's surprisingly nice. You basically can just like define a library. I think it just gets dynamically loaded into Python. And so you just define a main method which registers some types, and then it's just like, oh, here you go. And so that's what we do. So basically, at library initialization, we do this dynamic registration where we say, well, dynamically create a Python type object from this description and register it with Python.
Why do we need to create these like pointers that we're going to like allocate the memory for later? Why do we need to like create them ahead of time and as opposed to just creating all of that
Good
at
question.
runtime if that's when we can use it?
Good question. I'm not sure if we do anymore, but if we do, it's because to say construct a new one of these, you need to know the type object pointer because it's like to invoke a type constructor, you need to have the type. We also may do other things with them, such as constructing the type hierarchy, which involves like referring to them from different places of the code. So that's why we want a global list of these pointers.
Okay, makes sense. Thanks.
All right. Any
I'll
other
go
questions?
ahead. I was going to say, I'll go ahead and stop the recording.